Hello, welcome to the talk CQRS. Do you really need two databases? Over the next 30 minutes, I will try to give you insight into what is CQRS, what is motivation behind CQRS, and why would you actually want to use something like that. So first, let me go with the basics. We are all developers, well, most of us are developers. What is our job? What we are doing on a daily basis? And first thing that might come to your mind is that we are building systems. We are developing application systems, putting them into production. However, if you look at the typical life cycle of an application, you will see that you might be developing application for 6 months or 9 months or 1 year, and then you put it in production, you release it, and there will be maintenance period. And this maintenance period can be really, really long. So actually, when you think about it, what we are doing is not building. We are maintaining our applications. We are responding to change. We are listening to our users. And based on their feedback, their wishes, their requests, we are changing the software. So you could say that our primary duty is not to build systems, but to change them. And of course, changing software, implementing change requests is something that almost none of us love. Why? Because changes are hard. So I will start from there, and I will give you context why you would want to use, or why you may want to use something like CQRS to make changes easier. In order to understand what is making changes hard, I decided to use so-called Cynefin framework developed by Dave Snowden in 1999. This is framework for analysis of business systems, but of course, this can be applied to any kind of system. So, Dave Snowden analyzed systems and concluded there are 5 manifestations of a system. So systems can be obvious or simple ones, complicated, complex, chaotic, and disordered. Disordered is category of the systems that cannot be positioned in any of these 4 categories. So let's look one by one of these systems and let's analyze them. Let's see what is going on there. Because in the end, we're going to build such systems, we're going to maintain. So first category are obvious systems. In these systems, you have very little information, very few variables. You have direct cause and effect relationship. So you do something, there is direct consequence. And you could use simple rules to describe this relationship between the cause and the effect. So you could say you have predictable effects here. And this is the domain of best practices. Obviously, these systems are very simple, very easy to develop. This is something you could think about it as something as you develop over 1 weekend. So very simple hobby projects. Well, then comes the next category, complicated systems. And you could say that these systems are opposite of easy. You have a large amount of information, a large amount of variables. You have complicated relationship between the cause and effect. And actually, this is domain of experts. When I say domain of experts, I don't mean expert developers. I mean that this would be typical business application that you are building, and you need domain expert in order to understand the rules and implement system that would digitalize the business. Expert will consult you on. So if you're building an e-commerce system, this would be typical example. If you're building banking application, you need banking expert who will tell you all about the domain, and you will implement. With these systems, we can apply design patterns, good practices, and this is what most of us professional developers are tasked with doing on a daily basis on our jobs, in our workplaces. And then we are proceeding to next category of systems, and these would be complex systems. You could characterize these systems as opposite of simple. So these are systems which are not simple. And you can see increasing level as I'm proceeding with obvious and complicated. Now I'm covering complex systems. Things are getting hard. So with complex systems, you can see this is blue circle in unordered column. We are now entering domain of unordered system. When I say unordered, there are no rules. You can look at these systems and imagine that you arrived at a new workplace or you inherited project from someone, and now you're trying to find your way in software project that you're going to maintain. And you are faced with unmanageable amounts of variables, information, factors, dependencies. It's hard to establish relationship between the cause and effect. And this is typical situation where you would fix a bug, and fixing a bug would produce another bug or another 2 or 3 bugs. We all know these systems. These systems are systems where it's very hard to plan, it's very hard to predict. You are assigned a task, and you simply cannot say how long it will take to be implemented. So this is very unpleasant situation for us developers. And these projects is something that you explore and try to probe. So if I change something, what will be the effect, etc. Final category of systems are chaotic systems. And I won't talk about them because this is a place you don't want to be. And usually software projects are not chaotic. So in most of the cases, you will be working on a project. If it's greenfield project, if you're starting from very beginning, you will be building complicated system. And over the months and years of building this complicated system, you will slowly transition into complex systems. So as software system is becoming mature, you will be moving from the domain of complicated to the domain of complex. And where you want to be is in complicated domain, because this domain is complicated because there are complicated business rules. Business domain, which is non-trivial complicated. So essentially, when you look at complexity, you could divide it into 2 categories. And this was described in a book or essay, long essay, No Silver Bullet, by Fred Brooks in 1986. He analyzed complexity of software systems, and he concluded there are 2 types of complexity. First is so-called essential complexity. This is the complexity of the domain you're implementing. So if you're implementing banking software, you have to follow banking rules and regulations. This cannot be avoided. This cannot be changed. This cannot be altered. These are domain business rules, business scenarios you need to implement. We cannot do anything about this. However, there's another type of complexity called accidental complexity. And this is not the complexity of domain anymore. This is complexity of our implementation. So total complexity of software system we are working with consists of essential complexity and accidental complexity. When accidental complexity is close to 0 or very low, you have this orange circle complicated system. As accidental complexity grows, you are slowly moving to the blue circle complex system. And when I say accidental complexity, this is complexity again of the implementation. This means classes, inheritance, dependency injection, various hierarchies, data structures. So what is our goal? Our goal is to minimize accidental complexity. So in order to do that, we can turn to something ancient like mathematics. Mathematics is mature, very well-established field of science. And you have some rules here. You learn them in elementary school. Look at the square root function. Imagine me calling square root function in mathematics with arguments 25 and argument 9. every time I call function, or every time I take square root out of 25, I will get 5. Every time I take square root of 9, I will get 3. And this will always be the same. And it doesn't matter if I first take square root of 25, then 9, or if I turn this around. And you can probably already see where I'm going. I'm describing some good properties of the mathematical functions, which help to establish very solid foundations in mathematics, so the researchers can build structures on top of it. Functions in mathematics have some good properties. There are no side effects. What this means? What is side effect? Well, if you have a square root, effect of the square root is computing result. Side effect would be something additional that this function does. But square root is not doing anything else. It will take x, which is 25, for example, it will return 5, which is value of the function. And this means that mathematical functions are deterministic. For the same arguments, they will always return the same result. And these two properties, lack of side effects and and deterministic function, is called pure function. So pure function is a function that has no side effect and is deterministic. And as a result, in mathematics, you have something called referential transparency. This means when you have expression square root of 25, you can replace it with computed value 5, and everything will be fine. So in ideal case, programming would be on this level, same as mathematics. However, when you look at the functions or methods in programming, we all know, and you will see, that we can have side effects. Most times, functions or methods in programming are not deterministic, meaning if you call them 5 or 10 times with same input arguments, you may receive different result, and you will probably receive it. Programming functions are impure, so they can have side effect, and they can be, or they are, non-deterministic. And of course, a lack of referential transparency because of all of this. All of this can be boiled down to the fact that functions in programming are not isolated. They are communicating with the environment. So they are either reading from environment, and that would be, for example, reading from a database or reading from the keyboard, or this interaction could be modifying environment, generating side effects. And you can say that output on the screen or saving to the database is a typical example of the side effects. Side effects are not inherently bad, because without side effects, we would not be able to communicate with the world. We would not be able to print things on the printer, on the screen, send emails. We would not be able to read keyboard. However, when you look at some consequences of side effects, you will see that functions or methods which are showing side effects are unpredictable. You cannot tell when you call it next time with certain arguments what you will get back. It's hard to reason about them. So this is part when you arrive at the project, which is 2, 3, 5 years old, and you have hard time understanding what is going on. And testing is also hard. Reusability, which should be goal, it's very hard. Because if you take a function or method and bring it from one project to another, or component, you cannot be sure it will be working in the same manner, because it was in the old original project, it was relying on environment. Concurrency is also very hard. We all know that. Composition of functions, which is nice property, is also almost impossible with side effects. And it's hard to refactor. You remember, old rule, if it works, don't touch it. So if this is the rule, this means that we are very careful about touching working code. We are afraid to refactor it. And of course, also debugging is hard, because the code you're working in could be reading from the memory, from the database. Sometimes it's very hard. There's interesting property or a name for methods which are honest. So honest methods are giving you a clear picture from the declaration what they are doing. So methods with side effects are dishonest. You cannot read from the declaration everything that is going on. Maybe exception will be thrown, but you do not know that until you start reading the code. And also, what can happen is that if it's reading from the database, not all input parameters are present. So, in other words, functions, methods with side effects are hard to understand, hard to work with, hard to refactor. And when we look at something that is called stereotypical architecture, this is type of a project we all started developing when we were junior developers. And you have some kind of a client which is talking to application services, sending data transfer objects with some data, application services responding back with response. Application services are working with domain objects, modifying them, mutating them, saving them to the database. This is something we all started with, and this architecture on complex domain projects will lead us to the problems I already described. So over the years, our colleague developers figured out that there's a nice way to structure projects. Bertrand Meyer, in his book, Object-Oriented Software Construction, introduced something called CQS. What is CQS? CQS is Command Query Separation Principle. And this principle states that you should divide all your interactions with your system into two classes, two categories. One of them is commands, the other category are queries. So commands you send commands to the system, and command will change the state of the system, and they will not return anything except for, okay, I executed command. The other category are queries, which will return result to you, but will not change the state of the system. Again, I'm mentioning that this is something that was reached empirically over many, many projects. People converge to this approach. And these two principles of commands and queries could be simply formulated as a rule. Asking a question, which is query, should not change the answer. In other words, queries should not produce side effects. And that means that we just eliminated side effects from, let's say, half or more than half of the methods we are building. This principle is applicable to the surface or the interface of your application. So, if you apply CQS principle to your application, you will get following architecture. So now client is sending either command or a query. Command will be accepted by app services. Command will mutate domain objects and store them to the database, and that's it. Or client can ask a question, send a query, and then app services will perform a read-only operation and return result to the client. So this is tiny change. We are just changing the way we are talking to our systems on the back end, but this can have profound consequences, as we will see a bit later on. And people starting working with CQRS usually ask questions like, okay, I say something to the database. Database will create primary key, and I will get primary key. So I'm violating CQS as a principle, or can I pop the value from the stack? Because popping value from the stack is both fetching information of the top member of the stack, top element on the stack, and also changing the state of the stack. And of course, the answer is this is just a principle. It's not our goal to reach perfect state of CQS. Our goal is to build simpler systems. So yes, these two scenarios are quite possible, and you should never follow this as hard rule. This is just a principle. So be pragmatic. And following CQRS, there was evolution of this idea, and then Greg Young in 2010 came up with CQRS. CQRS is short for Command Query Responsibility Segregation. So with this principle, we are now propagating from the surface down the backend project. CQRS operates at the level of the class or method. CQRS now operates on the architectural level. In other words, CQRS will separate the entire subsystems you are building into parts which are handling commands and parts which are responsible for handling queries. And typical CQRS architecture would look like something like this. Now you see that this separation is penetrating and slicing complete backend of your application. And you are ending with part of your application which is accepting commands, mutating, changing domain objects, saving them to the database. And then you have on the query side, you're just reading. Very simple, very performant operation of reading from some kind of thin read layer, which can be cache, this can be pre-computed projection, this can be Redis, whatever works for you. And you have effect of so-called eventual consistency, because now when you execute command, change state of the system, it will take certain amount of time to propagate this to the read model. But I will cover that in the end. So consequences of organizing your application in CQRS architectural pattern is that now you have better scalability because reads and writes are separated, so you can use different approaches for your reads and writes. You are more flexible when you need to optimize something because, again, if you have many reads, you will not have to refactor complete application. You will have to handle refactoring of just this slice, which is handling the reads. It's also much more simpler with the complex business logic because when you're writing to the system, you need to check permissions, you need to check various kinds of authentication, authorization, etc. And this can be isolated from the read side, and read side can be very simple. And also security becomes more granular. Now your commands and queries can have different security policies. Greg Young applied CQRS primarily for event sourcing, and on the screen you can see typical diagram for event sourced applications. Event sourcing is a way of programming where you are not storing the state of your system. You are storing events which are changing the state. And you can see in the upper half of this diagram that command will be transmorphed into one or more events. Events will be stored in some kind of event store. And then based on the event, you will fold and compute these events to compute the state of the system, which then will be read by the query. And you can go and use different pragmatic approaches with CQRS. So what you can see now is so-called caching flavor of CQRS. You're still on the command side. You're mutating your objects, you're storing them into storage, but then you compute view models, read models, and put them into Redis. And think about how performant Redis is. This means that you can easily handle heavy load of queries, read requests on your system. We just solved something that can be very hard problem. You should be pragmatic. So maybe you will need 3 databases. What you can see on the screen is a technique where I'm using 3 databases. First one is for storing domain objects or domain entities. Then I'm computing projections or view models, putting them into another database. And let's say on this project, I need full text search. So I'm using also Elastic cluster, and I'm populating also things inside of the Elastic that needs to be searched. So I'm being pragmatic. I'm using appropriate solution for specific problems. Because if I'm, let's say, storing projections into a relational database, full text search becomes a hard problem for me. So I will introduce Elastic for specific feature of full text search. Or you may go with something like RavenDB. In this diagram, you can see I'm still using CQRS, but with just one database, single database. RavenDB is quite interesting because internally, RavenDB has, you could say, two databases. It has key value store, so domain objects that your commands are modifying will be stored inside of key value store inside of RavenDB. But then, every time you change entity or document inside of RavenDB, indexes will be updated. And when you are reading, when query comes to your system, RavenDB will deliver answer to your question or to your query from indexes. Again, we are being pragmatic, and we are using in this specific architecture this nice structure of RavenDB. So you can see that I'm still using a single database, but I'm enjoying all the benefits of CQRS architectural pattern. And there are some additional scenarios where CQRS is working fine, and unfortunately today I don't have enough time to check them, but check actor model. I think this is the future of concurrency. If you're using async operations, CQRS is a perfect match for you. If you're using microservices as well, whenever you have disparity or high difference between number of reads and number of writes in your system, CQRS is something that can help you optimizing separately these two verticals in your application. So very versatile technique. Eventual consistency, you saw this red line, and you may be thinking, okay, I'll be writing something to my database, and then my query will be reading from another database. There is some time needed to propagate. Well, it turns out that in a typical business application, 90, 95, maybe even 98% of the scenarios are not requesting immediate consistency. And in turn, this means that you can use async execution of commands, which will increase capacity of your system. And yes, even though Greg Young introduced CQRS along with event sourcing, of course you can use CQRS without event sourcing. You saw a couple of diagrams showing you that. There are no rules. You can use either SQL or no SQLs. It's up to you to be pragmatic and choose whatever works best for you. And one more thing, if you're using domain-driven design, if you're designing with aggregates, you don't have to store aggregates. You can create projections right away. Projections are read models. So again, be pragmatic. There's no silver bullet, like Fred Brooks would say. So CQRS will introduce certain level of complexity. You must think in which circle you are. Do you have simple, obvious project, or you have something complex? Because CQRS will not bring any benefit to simple CRUD applications. And of course, eventual consistency is something that is not a problem, but you should be aware of it. That was all. I would like to hear any questions or comments if you have them.